Hello guys and welcome back to my channel. Uh, Today we want to cover the linear MOSFET application. So MOSFET linear region, linear or ohmic region. So we want basically to make the MOSFET behave like a variable resistor. Now, as you remember, the MOSFET as a semiconductor, it has 4 regions of activation. It can be, as you remember, if the VGS is higher. Sorry, my keyboard is bad. Okay, if VGS is higher than VTH is on, and then it can be in those 3 regions that you know. If VGS is lower, then VTH is off. This is as what you remember. Then it's better to explore this region graphically. Okay, so I will just plot the on region, the other doesn't interest. So suppose that we are here, so we are in the region which it is on, then we can plot the VDS over the ID current. This is the NMOS. Okay, this is the drain, this is the gate, and this is the source. ID is the current flowing into the MOSFET. Okay, and as you remember, the first region that's basically here is the ohmic region, and then you have the blue one, let's say, the saturation region. And you have a different type of function like this based on the VGS that you're using. So for instance, this is VGS equal to 1 volt, this is VGS equal to 2 volt, and this is VGS equal to 3 volt, and etc, etc, etc. Now, basically, the ohmic, basically in power electronics application, the MOSFET is not used as the same region as, for instance, an active load or an LDO. And why you know that? You know that because you can measure to verify it the VDS across the MOSFET, and when it is used in power electronics, which is PE, let's call it power electronics, it has basically these practical characteristics. Forget the theory, but the RDS on is very low, like 10 or 100 milliohms, not more than that, and the VDS is basically tends to 0. And in this switching behavior, the MOSFET behaves basically like on, an ideal interrupter, on or off. And when it's off, it blocks the is VDS of your basically of your back, of your boost, whatever. This is in the case of the back. Okay. When it is on, it has to block all this voltage here. But in the case of the linear region, we can have different types of application, but most of them is in the field of LDOs and current sources. Okay, we will explore these 2 types of application in 2 different videos. But before going on, you can actually found on the when you use the MOSFET in this region here, you can find something interesting in the datasheet, which is a plot like this. It's a plot where on the x-axis you have the VGS, and here you have the RDS. This plot is very important because it tells you two things. First, it tells you how the resistance varies with the VGS voltage, like here it's 5, 10, and as you can see, the resistance approaches a very high value when the VGS tends to VTH. Let me state this clearly here, because this is a very important concept. The graphic is something like that. And to give you some values, this can be like 0.1, but this can be even 0.3. This is like 4 volts, and this is like 10 volts. And this is the VGS. And that's also the resistance R on. So basically, when you use in power electronic application, VGS is kept high. But when you use in the linear region instead, since the meaning of the linear region is to use the MOSFET as a variable resistance, you want to keep the VGS close to the VTH, or at least around that. That's what you want. That's what you want, okay? So you want to create a circuit which basically behaves like that. To force a MOSFET in the linear region, you have to create a circuit which allows like that, because you cannot command the MOSFET to be like that, okay? You cannot do that. But you have to create such configuration to behave like that. It's not easy. So let's jump on LTSPICE. And let me open for a moment yes, for instance, a boost. Now, I don't care now that it's the boost of the previous video. What I wanted to show you here is, let's see if I have the datasheet of this guy. Let's see if I can find the datasheet of this guy. Datasheet. I'm pretty positive that I can show you the same. Yeah, this is pretty old, so it doesn't show any plot, but that's a pity. But by the way, so if you use the MOSFET, if you use the MOSFET like that, delete of this stuff, delete of all of this stuff, delete, 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 delete. You will see that the VDS during the period in which is not switching is basically 0. And now if you check the current here and you make the ratio between the current between the voltage and the current, you can find out what the resistor is, which is oh, sorry, wrong keyboard. When it's conducting, it's basically almost 0, 2.9 milliohm. So that's the resistor of this MOSFET. And in the database, it's written 2.4 milliohm. So more or less they are right. Okay. You can, of course, you can check this, and that depends. That depends also on the gate voltage, which in this case is 5, right? Yes, it's 5. Now I bet that if I raise this voltage to 10, for instance, this resistor would diminish. And that could prove what I was saying before. Let's check this one. Let's zoom in. 2.26. You see? So, as I was saying, this I could not find a picture, but as you can see, when the VGS was equal to 5 volts, the RDS was equal to 2.9 milliohm. Okay. Now, when the VGS was equal to 10 volts, the RDS is equal to 2.2. Okay. So you are basically in this case gaining more and more efficiency for free. Okay, because it costs you nothing to raise the voltage of the gate. But be careful, because in this plot of the resistor, when the temperature is higher, like 25 degrees or something, this resistor, of course, heats up, because, as you know, the curve of the resistor is double, so R0 equal to 2R, when the temperature is very high, like 150 degrees. So this is reasonable. But these circuits are made so that basically this resistor has this this MOSFET works as a perfect switch. But that's not the purpose of the today. We have to create a circuit so that basically it acts like a so that the VTH stays in the the VGS stays in the region of VTH, so that basically we act as a variable resistor. You cannot invent a circuit like that, and you cannot force a circuit to be like that. So basically you have to study some architecture. One of these architecture that is very, very famous online is this guy here. This is very, very famous. It's a voltage to current converter, and what you do is, in very short words, is to uh, keep is to control the voltage here, okay, and this is the resistor R, and the current will be basically V over R, where the V is the, let's call the VS, because that's the source of this guy. Because basically the op amp is being forced to, thanks to the op amp, here you have V control. Thanks to the op amp, you are forcing to have V control here, and the gate will be so that VGS will be around the VTH, because in that point of the graph you're gonna change the resistor. In this point you're gonna change the resistor. Here the resistor is basically almost zero, but here it can change drastically, like from 10 ohm to 100 ohm, even more. And here you are around the VTH region. So basically, when you turn on a MOSFET, you have to turn on completely if you want to use in the power electronic application. If you turn on not completely, but in this region here, you won't have a perfect conduction, and that's exactly what we need right now. Because the name of the project will be current load. Active current load. And as you can imagine, even few milliamps can generate hundreds of dissipation here. Okay, even if you have 100 milliamps, you generate hundreds of dissipation. So it is, of course, for granted that you cannot use normal MOSFETs. You have to use specific type of MOSFET if you really want to design this kind of load, this kind of active load. You have to put more and more and more of them in parallel. Okay, you cannot expect to work with just one. So the first thing that we want to create is our control central. Okay, so we use the op amp, of course, and as you can imagine, this will be the voltage Vs, which is this guy here. Let's suppose that we have 5 volts, and of course we want to make our control system, our central control. Okay, very, very easy. We will use a divider, a potentiometer. Now, do you remember the equation of the potentiometer in LTSPICE? You can basically say that you have a parameter x, and this resistor is Rx, and the other is R1 minus x. Okay, so basically it's complementary. Something like that. We can use a potentiometer, but we can change manually the resistor. Honestly, it's the same. Okay. It's not that we have a slider or something, so that we have still to do manually. So it's quite. So let's suppose that the user wants has a buck converter here, which we will create maybe later. I don't know if we want. as a buck converter, and from this guy you have like 40 volts. Okay, 40 does not exist. Let's use real voltages. 24 volts, and this guy generate. You want to test with I don't know 10 amps. Okay, so basically you have a 300 volts unit, more or less. Hmm. This is a classic in the industry. 24 volts, 48 volts are a classic in the industry of power supplies. So let's call this divider vcontr, which then will become a divider, and we will have this guy put it here. Let's we have to duplicate the system. Now I will use a random Mosfet for now, but because it's not the number that we care, but it's about the concept. Let's use a credible VDS. Okay, we don't care about the gate charge or anything. Let's just put a gate resistor, but we don't care about this gate resistor because it's not switching anyway. So and let's make, for instance, let's put a resistor here. Now, the way you can construct a resistor, you don't care. We just put like 1 ohm, just because, just because it's an example. But of course, you have to imagine in parallel this stuff in parallel. Now, just for the records, we can put more of them in parallel. Okay, just for the records to simulate at least let's put 3 of them. Okay, let's put 3 of them. Okay. And this is how you can build an active load. Now we have to suppose that of course we do have a buck converter here. So let's suppose that for now, without skipping all the switching stuff, you have 24 volts. Let's put a 100 milliohm resistor, and let's put a protection of a Zener diode of for the power for the active load. The active load has a Zener diode for protection. Let's suppose that it is in the range of, let's suppose it's very high. Okay, 68, 62 volts. And now, depending on the control voltage, so imagine that the user has a potentiometer somewhere in this active load, something done like this. Okay, here is the voltage displayed. This is the current displayed, something like this. And the system will display 24 volts. Let's use more credible. Okay, the system will display 24 volts, and it will display, like in this case, let's put 1K, 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 1K. So you have 2.5, 2.5, and 2.5. Will display 7.5 amp as a load. Okay, this is what the stuff will display. And of course, just for the sake of completeness, okay, just for the sake of completeness, here you will have the file drawing. The two circles, which you can change the load, you can change maximum load, blah blah blah, and then you have your connection. So let's run the simulation and let's see what happens. 1 million should be enough. Okay, so first vcontrol is 2.5, it's a divider. And this vcontrol is kept here, as you can see. So in this configuration, since we are changing the source, we are controlling the source, the op-amp will try to keep this voltage, will try to raise this voltage so that the VGS is always around the threshold voltage. You see, it's not completely turned on. It's not that his VGS is like 10 or something. So that basically now, how much current is flowing? 2.5 amps. You see? Exactly as we planned. But who is suffering in this system? The resistor? No, not that much. The MOSFET. Because the MOSFET, look at the VDS of the MOSFET. is 20. So while the boost, while it was conducting, the boost had 0 as VDS, and so the conduction losses. So let's compare these two stuff. The conduction losses in the linear region are very high. VDS is not 0, can be even 10, 100 volt during conduction. And the resistor is 10 ohm, 100 ohm, even more. And so in the instead in the other region, let's call it in power electronic region, in the power region, let's call it like I like it more to call it power region. The VDS during the conduction is basically 0, and the resistor, the ohmic resistor, is basically 0. Yeah, I know it's 10 milliohm and all the stuff. I'm working power electronics for 7 years or 6 years or something, so I know, I know. But to make a fast approximation, this is a very big difference, okay? And now this is acting as a current source, and this guy is giving minus 7.5 amps. So now you're sure that you're giving exactly. Now, this is a resistive load, actually, because I'm putting a resistor, okay? Um, and that's it, okay? So that's the first application as an active current load. Now we could technically, what we could do now, I don't guarantee that is gonna work, but what we could do is to create this box, okay, as an active load. So basically, all of this box is this. If I wrote 7.5 should be the same. I don't. Um, sorry. Before going on, if I increase my potentiometer, like for instance now, with 2K, the control is increasing, and now the current request is 10 amp. And so of course we have more current to switch. Okay, now we have 10 amp as a request. So let's see if it works with a buck converter. Technically, it should. Technically, technically it should. Okay, I'm not expecting any big surprises if I put a buck converter and ask a current like this. Okay, so let's build a buck converter. As always, let's do a boost. Let's do a boost instead because it's easier, it's faster, it's yeah, definitely. Dot param fs 250k dot param d 0.5. Don't even need of that. 0, 10, 1 nano, 1 nano, t on 1 micro, t period 2 micro. Okay, very fast, very simple. Okay, this is gonna be a very simple boost. Let's put 4.7 micro, and let's put 14 volts. Okay, and let's put here the diode. Let's put a big capacitor like 100 ohm, 100 micro, and let's connect the boost to the output. Okay, it's 0.5. It has basically no losses except for this guy. Let's put even one better like this. So I'm not expecting any big surprises. Oh, it's oscillating. Mm. Let's see if I can fix immediately that. Okay, probably because the diode is okay. It's probably because the diode is, yeah, it's definitely is it's probably because of the diode. Yeah, because it has basically has no reason not to work because everything is in place. 1 nano, 1 nano, 1 micro, 2 micro. Maybe we can slow down a bit, but I don't believe that's gonna change anything. VS, 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 V-contr, V-contr, V-contr. Should be around 20. It should be around. Okay, no, it's just slow. Okay, it should be around double the input. Okay, 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 okay. So it's working. It's working fine. It's working. Definitely, it's working fine. Okay, so nothing. Okay, so there's nothing wrong here. Okay, just checking. Just checking the. This is. This is definitely strange. Deductor is okay. I'm just fast checking this boost, okay? Okay, deductor is okay. Okay, for me it's everything is yeah, everything is okay. So there shouldn't be any kind of problem. Yeah, it's just a bit a bit a bit laggy. It's just a bit laggy. Because now let's connect this boost to the load here. Okay, so as you can, it's oscillating a bit. Let's see if this oscillation persists. Ah, no, okay, so it's only the transient. Okay, so it's only it's only an oscillation. No, because, okay, you are wondering why there is this oscillation. Okay, it's because when you have a resistive load, the resistive load helps to dampen this oscillation. But now, since it is open, since the MOSFET is an active load, basically, it just it's just free oscillating. Okay, and this is the oscillation between this guy and that guy here. It's an LC not damped. Okay, you can see that the frequency is very high. So let's see how much current this guy is draining. This guy is draining 10 amps. Okay, so it's working. Woohoo! So as you can see, we create all of this stuff just to create this. This should be equivalent to this. Let's put 10. Let's touch the guy, and should be the same. Yeah, it's lag. Oh no, I didn't close it. I'm just stupid. Yeah, but I don't know. Okay. Yeah, it's oscillating like before. So now, as you can see, we have created a boost converter. We have created a boost converter with the active load. Ah, don't worry, this is with an active load. So now I'm asking 10 amps from the boost converter. I can ask even more. If I wanted, I can ask even more. 27 volts because it's 0.5. Okay. And the current asked is 10 amps. It's 10 amps, but with this direction here, as you can see. So it's 10 amps on the positive direction. I can put like 10K here and ask even more if I wanted, like 30 amps. Yeah, you can design as you wish anyway, so this is an active load now. You can play as you want. Problem is that this guy is dissipating a lot. You see, this guy is dissipating like 90 watts. For this reason, to create an active load, you have to put more and more and more parallel of them. And of course, you have to protect the load, okay? You have to protect the load with a zener, which now is not conducting. So as we can see, it has like 1 microamp. But if we want to make it conduct a bit, let's put, instead of 62, let's put at least like 33. And you will see that in some areas it will conduct. Ooh, like here in the transient. But now, at least it has protected a bit. We can make even the guy even stronger at this is just for simulation purposes. just to see if the guy really clamps. Oh yeah, it clamps nicely. Yeah, unfortunately, like it's conducting like 40 amps, so so it's not feasible. Hey! It's not feasible. No, no. Yeah, I'm just playing. Okay, I'm just playing with the circuit. Okay, just playing with the just playing with the circuit. Okay, it's nothing. No, no, no. It's no, no. It has gone unstable. No, no, no. Let's put the xenon diode as it should. Okay, just conducting in the transient to help the circuit, and that's it. Okay, so now we have our 27 volts and the current. Well, guys, the video ends here. Thank you for listening to me, and see you in the next one. Bye.